Hey guys, today we are going to talk about limits as x approaches infinity. So the way that that's going to be written is the same as like other limits, except it'll have x approaches infinity on the bottom. That's an error. And then of like whatever the equation is, so f of x. So before we get into that, I want to review the horizontal asymptote rules because that is definitely going to come into play. So for big over little, which means like if the exponent in the numerator is bigger than the exponent in the denominator, that means there's going to be no horizontal asymptote. For a little over big, so the exponent in the numerator is smaller than the exponent in the denominator, the horizontal asymptote is going to be at y equals 0. And if it's same over same, then your horizontal asymptote is going to be whatever the ratio of your coefficients is. And so just as an example, then like if I was saying the limit as x approaches infinity for something like x squared over x cubed, then that's little over big because we have the squared on top and the cubed on bottom. So our exponent in the numerator is smaller than the exponent in the denominator. And the limit is just going to be where that horizontal asymptote is at y equals 0. And so the reason why we're reviewing those horizontal asymptote rules is because usually when you're asked for a limit as x approaches infinity, not always, but usually it means that there is a horizontal asymptote. And so you're going to want to know that, you're going to want to write it down or like whatever. But basically, so like if you had a graph and it's leveling off at y equals 0, then when x is approaching infinity, so that's like as you're going further and further right on the x-axis, then the limit is going to be where this graph is leveling off, so like where that horizontal asymptote is. And so that's why in that scenario the limit would be 0. So then I want to find the horizontal asymptotes for these three problems. And so keep in mind that's basically like, I said horizontal asymptotes already. We want to find the limits for these three problems. So keep in mind it's basically like finding the horizontal asymptotes. So starting with the first one, we have 2x cubed minus 7 over 3x squared plus 4. So that is big over little. And by the horizontal asymptote rules, that means there's no horizontal asymptote. So when there's no horizontal asymptote, then what you're going to say is the limit does not exist, or DNE. And so then moving on to the second one, you have 2x plus 3 all squared over 2x squared plus 3. So keep in mind whenever you are looking at the 2x plus 3 squared, that would really be 2x plus 3 times 2x plus 3. And so then if you worked all of that out, then that numerator really would be 4x squared plus 12x plus 9. And so then our highest exponent is still 2, and so is the highest exponent on the bottom. So that's going to be same over same. So then our horizontal asymptote is going to be at the ratio of our coefficients. So that would be 4 over 2, which is just going to equal 2. So then if we're writing that out, then we would say the limit as x approaches infinity of that whole thing there is going to be 2. And in our last one, we have 5x to the 4th minus 2x squared over 3x cubed. That's big over little again, so in that case, the limit does not exist. So then there's the other scenario where you're asked to find the limit as x approaches infinity. And the other scenario is when we have a geometric sequence or a geometric sequence. And so whenever you have a geometric sequence, for one, it's going to have to converge for the limit to exist. So that means that the common ratio is going to have to be less than 1 or greater than -1. So it has to be between -1 and 1. That's what this means whenever you have the absolute value of the ratio. So in the case where it's asking for about a geometric sequence, then it's either going to approach to 0 over time. So it's going to have that same like horizontal asymptote that one of the last problems had. Or the limit is just going to continue to get bigger and bigger or smaller and smaller, approaching either infinity or negative infinity. If it's doing that, then the way that we're going to say is the limit does not exist once again. So we're just going to look at these three problems, and basically what you're doing is trying to figure out if this geometric sequence would converge or not. So 1/2 to the x, the 1/2 is less than 1, so that would converge. So that means this one is going to approach 0. And our second one, our ratio is 7/3. Since that is bigger than 1, that's not going to converge. So my limit is not going to exist. So you would write D and E for does not exist. And in my third one, my ratio is 2. So the same thing happens here. That one is not going to exist. And so then I also went over to Desmos because I wanted you guys to see what these looked like on the graph. So I graphed each of these, and the one showing now is the y equals 1/2 to the x. So you can kind of see over here on this right-hand side that it is leveling off at 0. So since it's leveling off at 0, that's creating a horizontal asymptote there, and that is why on number 1, the limit is going to be 0. And then in number 2, you can tell it just keeps getting bigger and bigger, and so that is going to be approaching infinity, and so that's why you can say it does not exist. And in number 3, that's the same scenario. It is also approaching infinity. So you would say it does not exist for that one as well. So the last thing I want to do is just go over some different types of limit problems that you may see other than just asking you to find the limit. So this is actually a released NCFE question, and it's asking you what is the value of the limit as x approaches k from the left-hand side of f of x. So in our piecewise function, we have this weird function here, x squared minus k squared over x minus k, for when x does not equal k. But when x equals k, we just have 4 minus k. But we're looking for the limit, so it does not matter that when x equals k, we're looking at the function 4 minus k. So we're going to ignore that. We want to know what x is approaching, like as it's approaching k from the left-hand side. So we're using this x squared minus k squared over x minus k problem, where x is going to equal k. That's what we would be plugging in. But whenever we plug k in for x, this denominator down here is going to be k minus k, which is 0, so that's not going to work. So what we have to do is try to simplify this equation. So in that numerator, we have x squared minus k squared. And even though you don't normally see it like this, that's still just the difference of perfect squares because x squared is a perfect square and k squared is a perfect square. So that means that can factor down to x plus k times x minus k. And then we're still having that divided by that x minus k. And so then we can cancel out the common factors, which is this x minus k in the numerator and denominator, and that's just going to equal x plus k. So then now we need to take our x value, which is k, and plug that back in for x. So we would have k plus k, and k plus k is going to equal 2k. And that's going to be the limit as x is approaching k from the left-hand side. Or if it had asked for from the right-hand side, we would have that same limit of 2k. And then this is another type of question that you may see. So it's asking for what value of c does the limit as x approaches 2 of f of x exist? So for the limit to exist, then we need as x approaches 2 from the left and as x approaches 2 from the right to be the same number. So for the behavior around 2, for less than or equal to 2, we're using this first equation. When it's less than 2, that means that we're approaching 2 from the left. And then when it's greater than 2, we're using this other equation, and that's where it's approaching 2 from the right. So that means that we need these two equations to equal each other because we want them to be the same number. So we would have cx plus 1, and we want that to equal cx squared minus 1. And then that's going to be for the value of 2 when x equals 2. That's when we want them to equal each other. So what we're going to do next is we're going to plug in a 2 for x and see where that gets us. So we would have our c times 2 plus 1 equals c times 2 squared minus 1. And then I just want to simplify that. So my left-hand side, I have 2c plus 1. And it's equal to 2 squared times c, which is 4c minus 1. And I just want to solve now. So I'm going to subtract 4c from both sides, and I would get negative 2c. And then I'm going to subtract my 1 to the other side, and I would get equals negative 2. And now if I divide by negative 2 on both sides, I end up getting c equals 1. And so that's going to be c. So the reason why that works is because the limit has to be the same approaching from the left, which is this first equation, as it is approaching from the right. So that's why we set them equal to each other. But then we're only looking at the behavior where x equals 2. So that's why we're able to just plug in a 2 for x and then solve for c in the way that we did. So that's just a couple of examples of like more challenging types of limit problems. So just know that you may be able to expect to see that on like a test or a quiz potentially coming up soon.